Hi, it's Michael, and today we're going to take a look at how to create an observation plan for your telescope and evaluate the efficacy of that observation plan that you might be interested in executing on a multi-messenger event. And so if we start here from our home screen, within this we have what we call this recent GCN events, but basically here's a listing of the recent events that we've retrieved by GCN. And so we'll take as an example a neutrino event that came in something like a month ago here. And so on within this little panel, you can see what we call tags, but basically some basic information about the particular event. The fact that it corresponded to neutrino, it was one of these bronze track events that IceCube puts out. We have similar information available, for example, for gravitational wave events, the fact that this particular one was a neutron star black hole and the detectors that saw it. In the case of Fermi, indicating it's GRB, depending on the event, maybe it'll have information on short versus long, things like that. And so if we take the particular neutrino event here, we have some of that same information up at the top, when it is, and so on. We also include things like property lists. And so, for many of these sources, we will receive sort of information that will come out iteratively as the analyses are redone. And so those properties that come up will be listed here. In this case, it has a false alarm rate of, I guess, 2 per year. Energy, they have this signalness parameter that corresponds to how real do they believe it to be. And if you scroll down this page, you'll get the first panel of this analysis panel, and we'll come back to the analysis panel in a future video. But if you click at the bottom here, we have the observation plans panel. And so you can already see a handful of fields that correspond to a ZTF tiling for this particular IceCube event. We look back at the analysis panel and turn on the localization here. You'll see we have one of these really tiny IceCube localizations, and this is what these fields are currently covering up. Now, for the when it comes to making an observation plan, you have a wide variety of parameters available to you to make your plan. For example, this panel shows which fields are currently visible depending on their air mass, and you can specify different times in UTC that this corresponds to. And so if you can update this time for sometime late tonight. I'm really bad at UTC time, but something like let's say 4 a.m. and then you can update the calculation, and then in a minute this plot will update here, and so you can see that at 4 a.m. UTC, a handful of the fields are already observable. Because of course, so right now it's daytime in the US, and so nothing's observable from Palomar at this point. Going down the list, you can look at your allocations, and so in the last video we added a new instrument. Here I'll stick with ZTF for the moment. You can choose a localization, and so it's very common in these with these multi-messenger events to get a handful of sky maps or localizations that update on the minutes to hours time scale, and so you can choose the one that you want to base your observations around. You can choose the start and end date for these observations. The default is to just cover the next 24 hours, but it may be desirable to only choose the next couple of hours. For example, if it's already in the middle of the night and you only have a couple of hours left. This filter strategy indicates whether you want to, it's very common to do blocks of filters. Well, you'll first do, for example, G band, and then R band, and then G band over the entire field. You may want to interlace those, go G, R, G in each field in rapid fire, and then it'll be integrated. We have a variety of different schedule types. In general, these greedy algorithms basically look for the highest probability region to observe first. SEER here tries to take into account the fact that fields may be setting, and those fields won't always be the highest probability. Air mass weighted attempts to observe things when they're at the very lowest air mass, and so it'll wait for your high probability fields to be directly above. So depending on what the amount of time you have and your particular object, you may want different options there. In general, we have two different tiling strategies, and so the first is tiling, where you'll take your sky map and cover it with observations. The second is where you'll want to use a galaxy catalog. Perhaps you have a narrow field of view imager, and you'll want to take images of local galaxies, and so you have the options to specify that here. And of course, if you're going to use a galaxy catalog, you can specify that galaxy catalog there. And there's options for if you're using galaxy catalogs, how you want to order those observations. Do you want to emphasize bright B band or bright K band or star formation or what have you? Different parameters that galaxy catalogs can tell you. Now, the next parameter is exposure time. You need, for ZTF, we tend to default to something like 5-minute observations, but this is where you can change those observations here. For the filters, as I mentioned above, you'll often take observations in multiple filters for these localizations. A very common follow-up strategy for ZTF has been something like G band, R band, then G band. So we'll specify that here. You'll have the option to take a maximum air mass, i.e. you will not observe fields any below that particular air mass. Air mass of 2 or 2.5 is pretty typical. You'll have integrated probabilities, i.e. within the sky map, maybe you only want to observe the inner 50% of probability that you have. Or in this case, the default's 90%. Something like 90–95% is quite typical. We can specify the minimum time difference between observations. It can be very useful, in particular, to reject asteroids to ensure that you do not return to the same field within something like 30 minutes. And therefore, that's the default. You can make that larger or smaller if that makes sense for your particular search strategy. Finally, you specify some kind of queue name. We'll just call it test, for this particular case, and so on. And so you can give some extra information about the program. Since we're doing a neutrino follow-up, we can specify the neutrino program. Here, once you've specified all of your parameters, you can click Add to Queue, and then generate an observation plan. At this point, then your observation plan will start generating. I have our particular one that we specified down here. This neutrino program is here, and it'll be running, and it'll change to complete when it's done. I took the liberty of running this in advance so that we don't have to wait for it. Within this panel, you see basically the parameters that were specified for that particular search program. Perhaps it was done by someone else, and so you can see what other people have tried. You can see its status. Once it's complete, then you can generate summary statistics of that particular set of observations. And so in this case, it's a small localization, so we only had 9 observations. You're delayed only by 6 hours relative to the start time. when the observations would have started, the filters that this observation were generated for, the amount of time in seconds that was exposed for. So, something like 2/3 of an hour. The integrated probability, we cover basically the whole thing because it's such a small localization, and the area that you're covering to I guess cover the entire localization. So then from there, there's a variety of kind of tools you can use. You can have your little sky map here to see the 3 fields that you're comparing to. You have buttons here that you, in the case of ZTF and other instruments where you have the API set up, you can send it to the observation queue for ZTF in this case. We have this interaction tool. You can download a JSON file of the particular plan. You can create a little movie describing the observation plan. You can create what's known as an observing run, which we'll cover in a future video, but basically creates an instance where it'll kind of show the different fields that you want to observe. And then finally, you can create what's known as a sim survey analysis, but basically an analysis whereby you can estimate the number, for example, the fraction of the localization that you would find a kilonova in or a GRB afterglow or something like that. So we can take a brief look here. And so if you click on the sim survey analysis dropdown, it'll look kind of similar. You'll have options to choose the different localizations. You'll choose the different instrument that you're interested in. You can specify kind of the time range that's analyzed, the cumulative probability, which again defaults to 95% here, the number of injections you have, in this case 1,000, which is pretty reasonable for most localizations, the minimum number of detections. Maybe you want 2 to ensure that you can identify moving objects, for example, and change your detection threshold, so on. We have a couple of different models option here. So we have a 17 kilonova-like option. We have a GRB afterglow option, and you can change the maximum energy that afterglow has. You can specify some kind of linear model with either a rise or decay. This one has a peak magnitude of -16, kind of similar to 17, and then a decay rate of 1 magnitude per day. Once you specified that, you can click submit. And similar to what we've done before, I have a couple of options here. In this case, I've already created an afterglow model that has all of the parameters that go into the afterglow, the number of transients, the number in the region, number detected, and the efficiency. In this case, you detect all of them because it's the distance prior is set up in a way such that in this case you can detect all of them, but you can use this to evaluate what fraction of events that you should be finding for a particular event. In the case of the kilonova model, you find many fewer because it's intrinsically fainter than the GRB afterglow that we've set up. So anyways, hopefully this was helpful when it comes to making your future observation plans. And as always, we look forward to your thoughts, questions, and suggestions. And otherwise, good observing.